Good morning, everyone. Let's start with one question. Let me say the initial density matrix is Ix, and your Hamiltonian is given as omega I Iz. I want you guys to tell me after a time t, what will be sigma of t?
Ix cos of omega it plus Iy sin of omega it.
Plus I?
Y sin of omega it.
I'm going to give one more. So the initial density matrix is Iz, and the Hamiltonian of chemical shift is given thus. What is sigma of t?
IC because sigma 0 and Hamiltonian are both IC, so they will commute.
So that was a pretty easy answer. For initial density matrix of Iz, try different Hamiltonian. So let me say Hamiltonian 1 is omega I Iz. Hamiltonian 2 is omega 1 Ix. Hamiltonian 3 is omega 1 Iy. For all of this, determine what is sigma of t. I think the first one was just solved right now. We said there is no evolution that happens. The second one, yes.
Iz cos omega 1t.
Cos omega 1t.
Minus Iy sin omega 1.
Good job. It is important largely because we are going to keep using this over and over again. Louder.
Iz cos omega 1t.
Okay.
Plus I sin.
That's correct. So that is the first set of things. So now let's go to the second one. Let's say the initial density matrix is Ix, and your first Hamiltonian is omega I Iz. Can any one of you tell me what will be sigma of t?
Ix cos omega 1t.
Omega I t, okay.
Minus Iy sin omega 1.
Are you sure? Anybody else wants to give some other answer?
Plus Iy
Yeah.
sin 1
Plus Iy. Yeah. So go take a look. Maybe you made a mistake somewhere. It should be plus Iy. Okay. Yeah, but so far so good. I'm happy that at least people are catching up to the idea of what is being done. Thank you. So now let's go to omega 1 Ix. You're starting the initial density matrix that's along Ix, and your Hamiltonian is omega 1 Ix. Therefore, sigma of t is going to be equal to?
omega I comma is.
Therefore? Okay. Therefore, if say omega, Hamiltonian is omega 1 Iy, what should be sigma of t? If you started with Ix.
Ix cos omega 1.
We are looking at rotations about the Hamiltonian from the initial state that you have had. This is the same thing that we learned from the semi-classical picture. You started with Ix and you make a rotation along X, no change will happen. If you take a vector and rotate along the axis of the vector itself, you see no change. On the other hand, if you end up taking the vector and making a rotation any orthogonal to that vector, you're going to have a rotation about the axis in which you're applying the pulse. So that's essentially what is happening here. If you are able to think of X, Y, and Z. This will not work for two spins, but let's start with a single spin. Let's say you started with an Ix, and you can imagine the omega 1 Iz as a counterclockwise rotation about Z. So therefore, the vector starts to go here at an angle of omega 1 at an angle of omega 1 times t. So essentially what happens, the projection along X will be Ix cos of omega 1t plus Iy sine of the same angle that you have had here. So basically, all these are counterclockwise rotations about the pulse or whatever perturbation that you're applying. Of course, we are assuming the omega-1 here is time independent, which is what I want you guys to imagine. The idea that I had given about omega-1 is a constant V1 applied during the duration of the pulse. So far, omega-1 is time independent. For most of the course, we'll assume omega-1 is time independent. If it's time independent, then what did we learn? D sigma over dt, which has a solution of minus I by h cross Hamiltonian comma sigma, can have a solution which is given by e power minus IHT sigma 0 exp IHT, for which you have the Beckel-Campbell-Hausdorff expansion, which gives you the final solution. For a simple spin half system, you are able to realize, depending upon where you start and what you apply, the solutions are nothing but projections that are obtained following a mere counterclockwise rotation above the application of the pulse. Okay, so let me repeat again for the benefit of people who are not able to understand. The best way to understand it is to go back, apply the formula to see what happens when you end up putting all this. But slowly, all these have a pattern is what I want you guys to understand. And what is the pattern here? If you started with Ix, if I'm saying it's aligned along X, if you're applying something along Z, remember, this is the chemical shift Hamiltonian. For instance, in some way, if we have prepared the density matrix along Ix, which we know how to prepare, if you apply a 90-degree pulse along Y from equilibrium, you can prepare a Ix state. What happens when you have an evolution with respect to time, when you just have chemical shift is what we are trying to understand. In some ways, whatever we have written here on top is called the chemical shift evolution. Okay, so similarly, in this case, these two are actually pulses by themselves. You're able to realize if you have pulses that could be represented as omega-1 times Ix or omega-1 times Iy, where omega-1 tau p is the flip angle and Ix indicates the pulse applied along the X phase. In the rotating frame, Iy indicates a pulse applied along the Y phase. Right? So slowly you realize we are trying to write a formalism where you would have the representation of the Hamiltonian for pulses and delays. It's actually a chemical shift delay that you have left here. Basically, if you started from a given state, any application, whatever happens, ends up being a counterclockwise rotation. So let's try to take the second example. What is the second example that we have had here? The second example is what you started from an Ix state, and you're trying to ask, what if I apply something along omega-1 Iy? So the rotation will end up taking Ix along the minus Z, so therefore the minus sign starts to come up. Of course, since you do not know how long you're applying the pulse, the omega-1 t will take care of it, such that you're just writing Ix of cos of omega-1 t minus Iy of sine of omega-1 t. So of course, if you keep having a longer time, you would have a situation where the Ix would have become minus Ix. Those things, that will be a 180-degree pulse that's applied along the Y phase that's present. Did that make sense now? If you have an initial state, how does the initial state change with the perturbation that is being applied is what we are trying to understand from this given set of equation. Let me repeatedly say, this is for a time independent Hamiltonian. We'll see for a time dependent case, how do things change, but let's be comfortable with a time independent Hamiltonian first. Okay? Yeah? Okay, so let's continue. The only thing that is left in this case to see whether you guys have understood, let's say we start with the initial state along Iy. Let's apply the same thing that we have been looking at so far, where the Hamiltonian is omega Iiz.
Omega IT plus Ix.
No, this will be a minus sign. You are talking about a counterclockwise rotation. You started with Y, you are going to go to minus X, not to plus X. So please be very careful about it. This is where you think the understanding helps you, but sometimes your bias ends up clouding your understanding. So don't be heavily biased in way where you overconfidently state the wrong answer. Okay, let me go again. Now we are having the same IY state. You're applying a pulse along omega 1 IX. Omega 1 tau p could be some flip angle, and you're talking about omega 1 IX.
IY cos omega 1 t. Sin omega 1 t. Plus
We repeatedly said counterclockwise rotation, right? So last question.
IX cos
IX cos
phi t minus IZ sin IY.
Okay, just a moment. Let me write IY. Anything else?
No.
Good. All right, let me leave it at that. That's correct. It's just IY. There'll be no time evolution. I shouldn't write a 0. I should have written this as IZ. Okay, let's escalate it one level up. Let me say the initial density matrix is IX. I want you guys to take the next 2 minutes. If the Hamiltonian, let's take a scalar coupling Hamiltonian, weak scalar coupling Hamiltonian, which is going to be given by pi j 2 IZSZ. I would like to know after a time t, what will be the density matrix. Best way of doing this would be to write the BCH expansion and trying to understand what comes up. Yeah.
Ix cos pi j t plus 2 I by SC sin pi.
Good. So looks like you're practiced enough. So let's go stepwise. That's the right answer. The way this would work out is that you write the BCH formula where sigma naught is what you started with minus I t power 1 by 1 factorial times the Hamiltonian times sigma naught. The Hamiltonian here is pi j 2 IZSZ comma IX. Now, the question arises when you have an operator of this kind where you have to write IZSZ IX minus IX IZSZ. Right? That's the commutator that you're trying to look for. The major problem comes on how you can move one operator up front of another operator. If you guys might remember, we said whenever we applied the Hamiltonian, especially when you applied the 2 pi j IZSZ, let's say on the alpha beta state, you realize that we only operate the IZ on the alpha, only the SZ on the beta, meaning that the IZSZ operators commute with each other. What do we mean by this? I comma S is equal to 0. Is that right? They don't operate on any other states. They just operate on themselves. So therefore, you can literally change the order in which things can happen. So therefore, you promote IX to the front, and you will realize this reduces itself to IZ comma IX times SZ. The moment you end up doing this, is that right? Yeah. So therefore, you get IZ comma IX as the commutator times SZ, which is going to be IIY. And the 2 comes up because the 2 already existed before, nothing else. So therefore, this commutator reduces itself to something like pi j 2I IYSZ, where the small I is imaginary square root of -1. So similarly, therefore, I'm going to end up taking this to the next step, which is what is written here. It's going to be IT the whole square by 2 factorial, the Hamiltonian, which is pi j 2 IZSZ, comma, whatever was written here is moved here. Now, if you pay close attention, you have IZSZ and IYSZ being present. In both the cases, it's SZ. So therefore, I can literally write 4SZ square. In theory, I should not write it in front, but because I keep a formalism where I comes first and S comes later. So this kind of formalism is how I've written it. Yet again, if you pay attention, this is going to be something of the sort IZ comma IY. IZ comma IY is minus IX. Since you already had a I here, it's minus I square IX, minus I square will be 1. So it's basically IX is what remains. The important thing that will also remain is 4 times SZ square. What I want you to guys to raise your hand if you agree with me that you're okay with this cancellation. For some reason, I canceled SZ square with 4. Why did I do it?
4 times SC square should be identical.
I'm not able to hear you, but yeah, I think this is what you meant. Is that correct?
Yes.
Very good. Good answer. So if you are able to realize, we are implementing some of the things that we had learned earlier. SZ square is nothing but SZ times SZ. SZ, if you write as a polyspin matrix, you'll get 1/4 identity. There's a small issue here. You cannot do it as a 2x2 matrix, which we'll see a little later, but the logic is literally the same. If you take IZ square or SZ square, it will be 1/4 the identity. Just that the identity won't be 2x2, it will be a 4x4, which you'll see today or whenever we get a chance to look at. Okay. So therefore, the SZ square and 4 gets cancelled. You end up getting pi square j square Ix. So slowly you realize Ix starts to come back up again. Similarly, if you do the same logic in this part, you'll get 2 pi cube j cube Iy sz. Once again, you realize that 2 Iy sz comes back up again. And therefore, if you literally do whatever we did last time, take Ix outside and 2 Iy sz outside, you'll get a cos of pi jt, which is also the reason why I wrote the Hamiltonian as pi j times 2 Izsz and not as 2 pi j Izsz. That might confuse you in writing the 2 in the wrong place. So remember the Hamiltonian is pi j times 2 Izsz. Slowly we will realize that the 2 comes up as a normalization constant in front of the operator. So don't worry about that right now. So the correct way of writing a scalar coupling Hamiltonian is pi j times 2 Izsz, not 2 pi j times Izsz. Okay, so therefore you have Ix times cos of pi jt plus 2 Iy sine pi jt, where this is the sign expansion. I don't believe in this. So please be very careful. You can get the answers very quickly without having any understanding. So I don't believe in the fact that ends justify the means, because if ends justify means, then people won't understand what are the right means to do stuff. The right means to do this is to understand how does a density matrix evolve as a function of time? How does the BCH formula work out? When you end up putting it, you are slowly able to realize that you're invoking so many essential concepts that you have to know before going forward. Okay, so there is a way of doing this as well. But for this, we got to go to something like a 16-dimensional space. So you cannot imagine this in 3-dimensional rotations as you just saw earlier. Slowly you realize that as you start expanding your set of operators, you got to go to a higher dimensionality, meaning that I'm just going to draw it for the time being. Don't worry about thinking about this currently. So similar to the fact that you started with an Ix and you're performing a rotation, counterclockwise rotation about 2 Izsz in such a subspace, the third dimension will be 2 Iysz. How did we get this? Basically, if you end up getting the, let me think before I speak. If you end up getting the 2 Izsz comma Ix, what do you end up getting is 2 Iysz. So the third dimension that's orthogonal to whatever you started with will be 2 Iysz. Of course, there are still 12 other dimensions. So what all did we have to define here to get this? You had to define 3 axes and an origin, correct? You had 4 parameters to define the initial rotation. Similarly, for something where there is a coupled spin system, you actually have 15 such operators and identity matrix, which could be thought about as the origin. Okay, so in this 3-dimensional subspace with the origin, we are kind of negating the remaining 12 operators that exist. We don't have to see it because no change happens there, right? If you don't understand this, do not worry. What I request you guys to do today is the following. So for the initial density matrix Ix, we just did scalar coupling Hamiltonian where you had pi j 2 Izsz. This is the exercise that we just did. Please repeat it for your own sake so that you understand what's going on. Now, just change the operator to Iy and keep this weak coupling operator and find what is the answer. Then the next one is you start with Z and you determine what happens here. And similarly, you can try to show a few more things where, let's say, sigma of 0 is Sx and the Hamiltonian chemical, sorry, why did I write Cs everywhere? Should be J. Phi j to IZSZ. And most importantly, try to think about if sigma 0 is Ix, the Hamiltonian is omega s Sx, or rather Sz. What is sigma of t? Then you have sigma of 0 as, let me think, something like 2Ix Sx. Let's say one of the Hamiltonian is going to be 2IzSz. This signal. Okay, I can add a little more to this. So all this, I request you guys to go back and do other permutations and combinations. Okay, as Jeet said, let me give one more. Let me give an antiphase single quantum, sigma of 0 as 2Ix and the scalar coupling Hamiltonian. 9 to IXSX, the Hamiltonian as so these were the combinations. There are more combinations available. Your exam will be testing on some of these, more towards application rather than blind answers what you end up getting. Did the questions make sense? Okay, thank you very much.